Welcome to another episode of the Distributed Data Show, brought to you by DataStax Academy, where we bring you the latest news and interview technical experts to help you succeed at building large-scale distributed systems.
Hello, welcome once again to the Distributed Data Show. I am Jeff Carpenter, and I'm here with DataStax CTO and co-founder Jonathan Ellis.
Thank you, Jeff.
Welcome. We've been trying to get you on the show forever, and it's like, what's it going to take, Jonathan, to get you on the show? And he's like, you got to come to Austin. No, it didn't go like that.
That's pretty much how it went, actually.
So here we are, and we want to talk about Cassandra versus the cloud databases. Can I frame it like that? Too confrontational?
Oh, we can frame it like that, sure, yeah. What I wanted to do was take a look at kind of the state of the art in the industry for cloud databases with Amazon DynamoDB, with Azure CosmosDB, and Google Cloud Spanner, and say how far have these come in the last 6 years since DynamoDB was released, and how do they compare with kind of the best of breed open source database, Apache Cassandra?
Okay, good. Okay, so I totally want to get into it. Maybe before we kind of get down into the details about any particular database, are there points of agreement that are just kind of like everybody's operating or singing from the same sheet of music?
Yeah, I think there's a few places where the industry has evolved a little bit since I started working on Cassandra in 2008.
Okay.
So it's actually going to be 10 years later this year. And one of those is that when we were first building out Cassandra, one of the things that really scared people was this concept of eventual consistency. And they're like, oh no.
Oh, they're
right?
still scared. Yeah.
They're still okay. They're still
people,
scared.
yeah.
They're still scared. But there isn't a better way to accomplish what we want to accomplish.
Right.
So 3 of these 4 systems. So you've got Cassandra, DynamoDB, and CosmosDB.
Okay.
Those 3 all default to eventually consistent operations.
Right.
And Spanner's kind of the odd man out. I'll talk a little bit more about them later, but
Yeah. We'll save them. Yeah.
Spanner is all ACID all the time, so there's no eventual consistency. But I think what drove everyone to this conclusion, or everyone but Google's engineers, was if you're delivering full consistency, strong consistency all the time, that means your master node is going to be a bottleneck for all your operations.
Right.
And so it's the same reason that people who do MySQL replication, they do asynchronous replication to a slave, they serve reads from the slave to kind of offload some of that work from the master. So everyone's kind of moved to that model and said, hey, we can deliver better performance, more predictable performance, lower latency by accepting eventual consistency, at least as a default. All of those systems give you an option to move to a stronger consistency model, including Cassandra.
Yep.
But
you're going to pay for it.
You are going to pay for it, yeah.
Okay. So that's kind of the base level of agreement.
Yeah.
So
I think I could add a couple more to that list. Another one is that we kind of started this next generation distributed database around the tagline NoSQL. And that's never been a really good name to describe
defining yourself by what you're not.
Well, yeah, and if you look at what the query languages for these databases look like now, they're all basically SQL variants.
SQL variants, yeah.
And so CosmosDB and Spanner, they both come out and say, hey, we're SQL databases. Cassandra was a little more cautious. We said we're CQL for Cassandra query language.
Right.
But if you look at it, we're just as much an SQL variant as CosmosDB and Spanner are. We just made, we've all made slightly different tweaks to support what we're trying to do.
You won't find joins in there, but otherwise, there's a lot of similarity, to be sure.
Yeah. And then I think the other point of commonality is that everyone's kind of bottomed out that making users understand your partitioning model is the only way you're going to get good performance.
Okay.
And this is something that hurts people's brains when they're coming from a relational model, or in particular a single machine database where I don't have to care about partitioning. Everything's living on my database box.
Right.
But you you can't get predictable performance unless you understand when you're going to have to pull data from different machines, and that means you need to understand the partitioning models. So all 4 of these databases have built that into their DML, their data modification language, for specifying what does my data look like.
Okay, so you're saying there's agreement that you can't hide that or abstract that awareness away from your application.
Yeah. Yeah, and you've got some other systems that have tried to make that jump and tried to abstract that away, but I think by and large they've been less successful. So the main one that comes to mind is a research database called HStore that was productized as VoltDB.
Oh, yeah.
And the problem that they ran into was, with the database abstracting that away, it's very confusing to their users when. For reasons that aren't clear to them, their performance gets cut by 2 orders of magnitude when it has to go do this cross-partition operation.
Why did this happen? Yeah.
So what HStore tries to do is it looks, you tell it what your queries are going to be, and you give it your data model, and then it says, okay, I'm going to infer the best partitioning for you to be able to pull data out that's accessed, that's joined together frequently to allow you to pull that out from a single machine. The problem is that there are data models where there is no such thing as a single partitioning model that lets you do that for all your common operations.
Right, okay.
So for instance, if you have a Facebook post and you have a bunch of comments associated with that post, you might say, okay, I'm going to partition it by the parent post ID, and I'm going to put those comments in the same partition. So now when I say, fetch me the post and its comments, those come out together. But now what if I also have a requirement where I also need to access comments by user ID? I need to be able to show me all the comments that Jonathan made today. Now I can't do that with that same partitioning scheme.
Right. Okay. It's that second and third and fourth access pattern that are going to start to destroy you.
Yeah.
Okay. So that's good. Level of agreement that we think we have in industry now on this thing. How does Cassandra handle these kind of issues? Like if the issue is how do you get to good performance at scale in a distributed database?
Yeah.
What's Cassandra's answer?
So Cassandra's answer is when you create a table, you give it a partitioning key, and that's going to be the first element of your primary key. That's just how we've defined it.
Right.
And then all the other columns in your primary key, we're going to sort the data, the rows within that partition. We're going to sort them by those other columns that you gave us. And so what that does is it gives you a very predictable performance model where I know that rows at the front of my partition, I'm going to be able to get those in basically constant time. And then you can say, well, I want it sorted reverse chronologically instead of chronologically because I'm going to access the most recent rows first. So it gives you a very predictable performance model. And then, so that's something that Cassandra's always had.
Right.
And then more recently, one of the problems that we ran into was, if that's your only construct is I have partitions full of rows, I'm going to have trouble with that model I just mentioned of I want to pull out data that's associated with each other in a single operation.
Okay.
And so what people were doing in their Cassandra applications was they were basically doing joins at the client side. They're saying, pull me out the user that I need, grab me a list of his forum posts, grab me a list of the comments, and each of those 3 operations is another query.
Or you have to do a denormalized operation, and then you're writing all of your comments to multiple different places in a denormalized model, et cetera.
Yeah, but even if I'm denormalizing it, even if I have a separate section of those comments that's for each of those access patterns, I'm still needing to fetch from each of those 3 tables.
You would still have to do a read before write in order to populate your denormalized tables, so it's just a mess.
Yeah. Yeah, and I can't always do it asynchronously either. I can't always say, give me these 3 and parallelize those because if the information I'm looking for the comments depends on the forum post that I'm pulling back, then I need to block on the one before I can get the other.
Right. So you're going to tell me that we fixed this.
Yes. So what we did was we said we need to find a way to nest data within a single partition
Yeah.
so that I can pull those back with a single query to a single table. And so that's where we introduced collections, and then we introduced user-defined types that allow you to nest more complex data structures inside a Cassandra row. So it's actually isomorphic to a JSON document. And we even added syntax to CQL.
Oh, there's an API, that's right.
Yeah, we even added syntax to CQL that says you can say select JSON, and it'll take that row with its nested collections and nested user-defined types and give you back a JSON document. Or vice versa. You can say I pulled off this JSON blob from my microservice and I just want to throw it into this Cassandra row. Cassandra will take care of parsing that apart and storing it appropriately in your schema.
I don't know if people do take enough advantage of that feature actually, because you could really have a really simple microservice implementation, as you said, and I don't see that happening as much in practice as maybe it should. Maybe it's a lesser known feature. I don't know.
Yeah, I think it's one of those things that's a little bit underappreciated that not too many people know about.
Okay. So great, Cassandra's awesome. We would say so, but let's talk about some of these other databases. You want to start?
I want to spend just a little more time talking about why Cassandra's awesome.
Oh, okay. No, please. We can do that all day.
Yeah. So part of it's awesome and part of it's different, right?
Okay.
So I said we've got a lot of consensus around some of these things, and we've got some things that there's less consensus around. So Cassandra's bucking the trend in that it requires a strict schema. So the other three databases we're going to talk about are all schema-less or very flexible on their schema.
Yeah, okay.
And Cassandra says, no, that's the wrong way to do it. You should tell me what data to expect, what the columns are going to be named, what data types are going to be part of those columns, and that way, as the source of truth, Cassandra as the database can validate and reject malformed documents or malformed inputs. And so there's actually a fair amount of research in the industry now that schema-less databases have been fairly popular for a few years, showing that if you have a single team that has a single code base accessing the database, you're good. It doesn't matter. The code is your schema, and there's nothing wrong with that. But once you expand beyond that to another team accessing it, maybe with a different language, maybe your Ruby on Rails app now it has an R application going through and doing some statistical analysis. Successful applications start to grow. They grow in terms of the teams that are dealing with them and the access client APIs that are used. And so I think it's inherent that you do want your database providing that level of stability.
Okay, I gotcha. Yeah, that makes absolute sense. I mean, I have architect alarm bells going off in my head when you're talking about multiple applications accessing the same tables. We all know that happens in practice. I always said no as an architect to that, but that stuff happens, right?
Yeah.
So, excellent.
And this is an area where it's actually an easier sell to our enterprise customers. They kind of get that. They're like, schema-less? Yeah, that scares us too. But so it's interesting how different parts of these scare different people.
Gotcha. Well, we don't want our operational database becoming just as disorganized as our data lake.
That's kind of a backhand to multiple audiences, but yeah, well done. So then the last thing I'd call out on the Cassandra side is that we added materialized views back in 3.0.
Okay.
So this is 18 months ago or so, which allows you, so you mentioned that you do need to denormalize to fit your different query patterns in Cassandra because we don't give you joins to do that.
Until.
So materialized views is a way where you can tell the server, I want you to maintain this denormalization for me, rather than having to do it in application code.
Okay, so there's a lot of shade that's been thrown at the materialized view implementation in Cassandra 3, though. So
yeah. So there's been a little bit of drama on the mailing list. And so there are some rough edges with the design. I'll acknowledge that. But so first what I'd like to say is if you're using them the way they're designed to be used, then they're very powerful, they're very stable. DataStax Enterprise Graph uses materialized use pervasively. We're very comfortable with that.
Right.
But we did make some mistakes designing them, and I would say that one of the main mistakes that we did was we made materialized views asynchronous with respect to the base table.
Okay.
And so there's no guarantee actually that
Right.
after I've written to the base table, Cassandra says, okay, we're good, and now I go and read from the materialized view. Yeah, it could be a while, and so that's a mistake because that, understandably, we've given people consistency levels in Cassandra where I can say I'm doing quorum, so I should
Right.
always see my most recent data. But now you're saying you added
Except your
materialized
view
views.
is not governed.
Exactly.
Okay.
So the reason we did this, there was a method behind the madness. The reason we did this was we thought about what if the user creates dozens of materialized views. Now if we make that synchronous, I'm going to be touching essentially every server in my cluster. If you have a dozen materialized views times 3 replicas, 36 replicas I'm touching. That's going to.
Right.
So I'm potentially compromising my availability if you say I want to make those synchronous. But
Right.
I think that was the wrong thing to optimize for. And if you look at other systems, I believe, if I remember correctly, DynamoDB's global indexes, which are similar in spirit to materialized views, I believe there's a limit of 5 that you can define. So there's other things that you can do besides just accepting that users can do crazy things with the system.
That might be one of those cases where a hard limit is advisable. Okay, so you brought up the topic of DynamoDB. You brought it up. Do you want to dive into that more?
Yeah, let's start talking about non-Cassandra systems. So in my talk, I tackle these chronologically.
Okay.
And so Cassandra came out in 2008 was the first release.
Yeah.
DynamoDB's first release was 2012. So that's next chronologically. So this is actually I said we all agree on a bunch of things, and there's been an exception to just about everything I've said that we all agree on. DynamoDB's exception is there's still very much old school NoSQL in terms of how you access your data. So you have a partition key and you have a sort key, but the sort key is basically an index into the map that your partition represents.
Okay.
So each partition is a sorted map of stuff, of values. So DynamoDB's nomenclature is you define tables. Tables contain partitions. Partitions contain items, and each item is a sorted map of tuples. So my beef with DynamoDB is, in 2012, I get it. That was adequate.
Right.
6 years on, Cassandra has nested data types. CosmosDB has nested data types. Spanner has a slightly different take on nested data types, but it's the same idea.
Right.
So with DynamoDB, you're still stuck in the bad old days of I need to make a query to every different table for everything that.
Still doing our application side joins.
Yes, I'm back doing client side joins.
Yeah.
But DynamoDB does have some cool features. I mentioned that they do have this global index.
Yeah.
So let me back up a second then and talk about that because it might not be clear what a global index is versus a local index. So,
Yeah, okay, please do.
Local index means that each storage node in the database is indexing the data that's local to that node. So it's in a partition database, that means you're indexing basically a random set of partitions. And so if I want to do an index lookup under that design, I need to do a scatter gather.
Yeah.
I need to ask every node in the cluster, do you have data matching this predicate?
Right.
And then pull it back in and compare nodes and say, okay, which results come first? So that means, and that sounds okay, like maybe you don't want to do that every query, but it sounds maybe okay. But there's a kind of a subtle gotcha, which is that if I'm big O of n, if I'm linear in the number of nodes in my cluster, that means that adding nodes to my cluster doesn't make local index lookups faster. Because eventually, and with Cassandra, it's about It's actually a fairly low number, 4 nodes. If you go from 4 nodes to 8 nodes, your local index performance is basically flat because now the dominant the dominant factor in your performance bottleneck is that scatter gather operation and not the local lookup.
Gotcha.
So Cassandra said we need to give people a way to repartition their data so I can go look that up by a key, by a column value that becomes a partition key under the new repartitioned data, and we call that materialized views. Materialized views let you do a little bit more fancy stuff because we can say, I'm going to let you specify not just how it's repartitioned, but I'm going to let you specify a projection. I'm going to let you say which columns I want to pull out of the base table.
Select a subset of those.
Yes, and then I can also specify conditions on it and say, I only want to materialize rows that match this other predicate. So global index is a bit of a simpler minded thing, but it's the same idea where I'm going to repartition it, and now my index queries scale as well as queries against my base table.
Okay. All right. So anything more to say about Dynamo?
I think that that's the highlights.
Okay.
So next, CosmosDB.
Yeah.
No, spoiler alert, this is the one I admire the most.
Okay.
They've done a lot of things right. And I think they took a look at Cassandra and they said, what can we learn from mistakes Cassandra made? Which is always a smart thing to do.
Yeah.
So one of the things that I think was a mistake that Cassandra made is we have too many consistency levels. So if you look at the DataStax documentation, I put into my talk, I pulled out screenshots of descriptions of the consistency level.
Right.
It's 3 slides worth.
Yeah.
Now there's around a dozen consistency
Something
levels.
for everyone.
Something for everyone. So if I'm looking at that now and saying, do we actually need this? I think it's fairly uncontroversial to say you don't need consistency level all. Because that means as soon as you lose a node, you can't do that operation anymore.
Right.
So, you never want to do that.
Right.
It's probably a little more controversial to say you don't need all of the non-local consistency levels.
Okay.
So we started off with quorum, and that says a majority of all the replicas. And then we said, you know what? Actually, when I'm in multiple data centers, I don't actually want a majority of all the replicas, because if I've got 3 data centers and 9 nodes, that means I need 5 of my nodes to reply, so I'm touching at least 2 data centers, probably all 3.
Right.
So we added local quorum, we added local 1, and those are what the defaults should have been. And so I would go as far as to say we don't need the quorum, we don't need 1. It should just be local quorum and local all.
Right. So this is
1.
interesting because maybe it should be more about the behavior that you desire from the application perspective than having to figure out or think about how many nodes are out there and where are they.
Yeah.
Right. So that is not where the session consistency level comes from.
Yeah.
I want to read my own writes. Can I just do that? Can I just read my own writes?
Yeah. So, this is rare, but it happens that a customer will come to us and say, "Hey, I'm reading against data center 1, but if I look at my network traffic, it's also reading from data center 2."
Yeah.
I will go out on a limb and predict you're doing a quorum read.
Yes.
And that's, it's doing what you told it to do, but that's not what you expected.
Right.
So, yeah, that was a mistake we made, I think.
Okay.
So CosmosDB says, okay, we're going to let you choose from a bunch of consistency levels, just like Cassandra, but there's only going to be 5 of them. And actually, I think that's actually probably still too many. DynamoDB says you're going to get to choose, on a write, you don't get to choose at all. But on a read, you can choose from eventually consistent or strongly consistent.
Wow. Okay.
And that's pretty close to the right level, I think, that people want to deal with. But CosmosDB has 5 with subtly different trade-offs. But they even put in their documentation 93% of their users of the operations are either bounded staleness or session consistency, and so everything else is very niche.
Yeah.
So I think if you looked at that, you could probably say you probably could have gotten away with 2, maybe 3. But
Let the market decide.
Yeah. But it is an improvement over Cassandra. Don't get me wrong. I'm saying it's not perfect, but they did better than I did 10 years ago. So can't complain too hard about that. Some of the notable things about CosmosDB. This is the coolest one, is that everything is indexed by default.
Oh, okay.
And so these are local indexes, but everything is indexed. And so there's very little information about CosmosDB's implementation.
Right.
Which makes it a little bit of an outlier because Google has published at least 3, possibly 4, if I remember correctly, papers on Cloud Spanner.
Yeah.
And Cassandra, of course, is open source. But there's actually very little on CosmosDB. There's very little on DynamoDB as well, but the documentation on DynamoDB is pretty first class. Like they have, you can infer a lot about what the system is doing because they've given you the details in the documentation to understand that.
Especially where they tell you the limitations, or am I going too far?
We'll talk about that.
Okay.
But yeah, I mean, there are limitations with DynamoDB that can be fairly painful, but to Amazon's credit, they're in the docs, and you can learn.
It's part of the SLA, essentially.
There's fine print, but there is fine print.
Yeah.
With CosmosDB, there's less of that, and giving them the benefit of the doubt, it's a newer product, and I fully expect their documentation is going to be fleshed out with some of these details as people ask questions about how does this work. There's at least a couple of the Microsoft PMs, program managers, on Stack Overflow answering questions. There's nothing nefarious about it. It's just a younger system. But the one place where they did publish a paper was about this indexing that they do. And it's really fascinating because what they've done is they've taken, instead of an exact index where if you have an index entry, you know exactly what documents contain that value. It's kind of a probabilistic thing where they say we're going to tune our index so that 99% of the time when the index says it's in that document, it's there, but the other 1% of the time it's actually not there. And so what the trade-off is, since some of the time it's not there, you need to do a 2-stage index read, right?
Okay.
You need to read the index that says it's probably in these documents, and then you need to read the documents and say, does it actually contain this term that I thought it contained? But by doing that, what they get for that trade-off is to index every column or every field in every document, less than 20% overhead in 99% of the documents across their data set.
Okay, that's a good
pretty
trade-off.
impressive. That's pretty impressive. And what that lets them do is it lets them allow arbitrary order by. So with Cassandra, I mentioned that you specify your sorting, how you want rows in a partition sorted as part of the primary key. So that's immutable. And if you want to sort an analytical query, well, you can do that with Spark and have Spark compute what that new ordering is going to be. But in terms of operational queries, if you want another ordering, you need another table to denormalize and do that ordering. So that's very powerful that having everything indexed by default means that I can order by anything by default as well. So that's a very powerful feature that CosmosDB offers. Now, if I'm going to look at what's missing, they don't offer any kind of denormalization, so there's no materialized views, there's no global indexes. So my conclusion is...
But it's probably coming.
It's probably coming, yeah. My conclusion is that Cassandra and CosmosDB are at rough feature parity. Cassandra gives you more powerful denormalization. CosmosDB gives you more powerful indexing. So if you're following Cassandra development, you know that there's a new index type called SASI that's been contributed, contributed by Apple, and that's a good option, but it hasn't been. That would actually let us do arbitrary order by or order by anything that has a SASI index, but that hasn't been wired up to the the query engine yet. It doesn't know how to leverage an index to do an
Right.
order by. It just knows how to leverage it to do predicate matching. So CosmosDB is ahead.
All right, so we have one database left.
So I'll tell you one thing that puzzles me about CosmosDB, and you can leave this in or cut this out.
Oh, okay.
There's something that puzzles me because they say that with respect to their multi-region story, that they support local reads and writes with asynchronous replication between regions. So far, so good. They also say that they support stored procedure transactions that are atomic within a partition. You can't do both of those at the same time. Because if I'm committing a stored procedure transaction and then saying, oh, we'll replicate it asynchronously, and then I'm doing the same thing in another.
That's not atomic.
That's not atomic
Right.
anymore.
Yeah.
So I don't know how to reconcile those two statements.
Okay. All right. Well,
It's a puzzle.
We'll have to let
readers can write in with the answer here.
We'll have to let that be revealed at a future
Yeah.
time. We have one database left to talk
one
about.
left.
Okay, so let's talk about Spanner. It's a little bit not like the others, if you remember the old Sesame Street sketch.
It is, yeah. So, and this starts at the architecture.
Okay.
Because Cassandra and CosmosDB says this explicitly, and I'm assuming it's true for DynamoDB as well. They're all dealing with, you have some compute nodes and you have some storage that's attached to those compute nodes that, I do the compute against. And so that's why you have these concepts of partitions, and you have limits on the partition size because I want to provide can keep my SLA, so I
Right.
can't let that get too big because it's tied to a specific core or a specific compute node. But Spanner's different. It's built upon Google's distributed file system, and so you've got blocks of file storage that can be mixed and matched and attached to compute nodes arbitrarily across Google's secret best in the industry network.
The network.
Yeah,
Yes.
and it really is that good.
Yeah.
Just as an aside, when we were testing DataStax Enterprise and Cassandra on Google's compute, they said, oh, all the storage is networked. We don't do local storage. And so based on our experience with non-local storage, we said,
well,
hang on.
anti-pattern.
That's going to be terrible performance.
Right.
And they're like, no, trust us. We know what we're doing. And as the performance characteristics, indistinguishable from local storage, nothing to complain
That's
about.
super interesting. Okay.
Yeah, so they know what they're doing there. And so they leverage that to build this this distributed database that's unlike any of the others. And so with Google, there isn't really a concept of I have partitions and rows within the partition. You just have, here's my partition key, and then that's all I need to care about. There is one limit. The limit is that you can have columns of up to 10 megabytes, and you can have up to 1024 columns per row. So that's you can have rows of up to 10 gigabytes, basically.
Okay.
That's the limit.
That's the limit.
But otherwise, there's no limits on how many rows are in a partition because the partition is the row. And then the way they do performant joins is they have a concept called interleaved tables, which is basically a way of saying this table over here, I want it to basically be a child of this first table, and so the storage engine is going to interleave, that's where the name comes from, the child data with the parent rows.
Okay.
And so when I do a join between two tables like that against the key that's co-locating them, then it becomes a local join. It doesn't become a cross, what we call a cross-partition join in one of the other systems. So really interesting design. And then the other part, of course, that we don't really have time to go into is how it provides full ACID using their true time mechanism and and Paxos quorums doing two-phase commit. So it's unfortunately, I think this is the most sophisticated and the most competent implementation of the wrong design. Because,
okay.
and the reason is that if you're saying I'm all ACID all the time, that is a really big price to pay whenever you do a write.
Right.
And even though Google's doing multi-Paxos and doing all the optimizations right, it's a very expensive operation to do two-phase commit across Paxos quorums.
And there's no other option.
There's no
you
other
can't
option.
opt out of it.
And so, just knowing nothing about it other than that's the architecture, you can look at that and say, writes are going to be significantly slower than in any of the other systems.
Yeah.
And so I didn't test this myself, and the test doesn't involve Cassandra, but Todd Lipcon, who is the main architect for Cloudera's Apache Kudu project.
We've talked about that.
Which is a columnar database that's kind of designed for what Gartner calls HTAP, hybrid transactional and analytics. So they benchmark. So the nice thing about Spanner is you purchase it by nodes. And storage. So you pay for your storage and you pay for your compute nodes.
Compute nodes, okay.
And a compute node is roughly equivalent to I guess an i3.4XL based on the pricing, something like that.
Okay.
It's basically $8,500 a year for a compute node is what it works out to. So you can do a fairly apples to apples comparison by standing up a node of Cassandra and one node's worth of Cloud Spanner and seeing what performance characteristics do I get for my money. And so Todd did that with Kudu and with Spanner, and Kudu's cranking along, ingesting 112,000 rows per second. Cloud Spanner's ingesting 4,000 rows per second.
Huh.
So,
and that's the full ACID transaction
yeah, that's
toll that you're paying?
Part of it is it's inherently slow because of that ACID design. In fairness, the Spanner engineers were communicating on Twitter and saying, well, part of the slowness is that it needs to start splitting these files across multiple storage regions, multiple compute regions. As you're pouring in more and more writes, we need to dynamically grow it. If you're familiar with HBase, HBase has this concept of regions, and then you need to split the region as you start adding data to it.
Okay.
And then one of the best practices with HBase is if you're going to do a bulk load, you need to pre-split the regions to get good performance.
Right.
And so Spanner, under the hood, it's got kind of a similar architecture. And so the problem is that there isn't any way to tell
you can't
Cloud
pre-split
Spanner
it.
to pre-split it.
Yeah.
So there's some implementation detail, but then even if they completely solve that problem, there's still the base problem of I'm paying this multi-Paxos or two-phase commit on Paxos quorums, and that's a heavyweight operation. There's no way around that.
Right. Wow. Okay. So anything else to say about Spanner?
I think that's the highlights.
Yeah.
Yeah, that's the highlights.
Okay.
So what I bottomed out with is I wanted to leave people with some
where does
recommendations.
this all end up?
Where does if I up-level this, where do I end up?
Yeah.
I don't see any reason why you would choose DynamoDB. It's just the limitations of not having any nested data, of having to do those client-side joins.
Right.
It's going to slow your product development down significantly. I do not recommend Spanner because of those performance characteristics that we just talked about.
Right.
So if I'm going to choose, if I were out there not working for DataStax, saying I need to build my company's next application, my short list is going to be Cassandra and CosmosDB.
Wow,
and then that decision comes down to, if I'm looking at the feature list, like I said, pretty similar in terms of the capabilities they give you. Cassandra a little more advanced here, Cosmos a little more advanced there.
Right.
But if it's roughly the same, why would I pick the one that I can only run in Microsoft's cloud? I mean, so that's a pretty easy decision for me. And with the footnote that, if I'm a hobbyist, or if I know that this project is never going to need to scale past 1 or 2 servers, then okay, yeah, I probably use CosmosDB for that. I don't need, because Cassandra itself, it's open source. You're paying for the infrastructure, but you're also paying for your time to operate it, right? You need
in your own learning curve.
And your own learning curve. Yeah, there's something there. If this isn't a project that I can afford to have at least a part-time DBA allocated to, then CosmosDB makes sense. But as you start to scale, then both you have the lock-in I mentioned, but just in terms of cost of ownership, you get a lot more for your money once you're starting to leverage that. Once you have tens of Cassandra nodes, even hundreds of Cassandra nodes, you make that investment in a DBA, you make that back pretty quickly.
Right. Okay. Oh my goodness, there's so many more directions that we could have taken things here. I want to have conversations about managed services and about what it means to be a multi-model database. And maybe if we get some reader mail and some suggested topics and questions, we can collate some of that and come back at you with another round. How about that?
That would be fantastic.
All right. Well, thank you very much. And thank you for joining us for another episode of the Distributed Data Show.
Thanks, Jeff.
Thank you for joining us again for the Distributed Data Show. We love your feedback, so go to the Distributed Data Show page on DataStax Academy and tell us what you think. You can also find us on the DataStax Academy YouTube channel or find our podcast on iTunes, Google Play, or wherever you get great podcasts. While you're there, make sure and subscribe so you don't miss a single episode.